Okay, we are in uh, Unit 3, Mechanical System, Rotational Rate. We did linear rate last week. Now, when you talk about rotation, that means something that is going around. Okay, I'm not making very good circles here, but goes around. It can either go clockwise or counterclockwise. All right, and we call that angular speed. All right, and that's equal to angular displacement divided by time. Okay, we'll show you a couple things here. All right, I already said the motion is either going to be clockwise or counterclockwise, and when we use the term angular speed, it's actually the same as angular velocity because it has to have a direction. You're either going clockwise or counterclockwise. That's your only choice. Okay, now the first thing you're going to notice here when we talk about angular speed, all right, you look at the variables. Now these are the letters that go into the equations. They are odd looking. You look at that. All right, that is actually an omega, and that's small. And what it represents is angular speed. One of the things that you find is that when you go from linear to rotational, you have the same equations, but so that you know they're rotational, they use Greek letters. So angular speed is going to be this funny looking. Kind of looks like almost like a curved W almost. All right, because there's a little opening right here. And then you have angular displacement, which is going to be theta. You've seen that before. All right, that represents an angle. And then T is time. Now, one positive is that English and SI are going to be exactly the same. All right, now the drawback is you're using some terms we've used before, all right, previously in the class, but we don't use that often. All right, we have radian per second for angular speed. Your angular displacement, or your angle in this case, is going to be radian, because if you remember, we practiced before that we had to convert from either a revolution or a degree into a radian. And then we have T for time, and it's measured in seconds. All right. Okay, so let's take a look at how we would do a problem. The second hand is on a clock. All right, they turn 360 degrees. 360 degrees means one full circle or one revolution, and it does that every minute. So we want to know, well, what is the angular speed on a clock? All right, well, we know the equation for angular speed. It's going to be angular displacement divided by time. All right, so now remember, revolution, what we have up here, we have degrees or revolutions. Remember what I told you before. You can't leave them like that. They have to be changed to radians. Okay, because unless you're using trigonometry, all right, you need to use it in a language that an equation will understand. See, that's the thing. When you're told, learn trigonometry, it's because it's in so many things. But if you don't have the background or you're not there yet and you're taking a course, this is the way around it. So you're going to take your 360 degrees. You know it's one revolution. So what we're going to do is we know the conversion is 6.28 radians is equal to one revolution. So we can use that as our ratio there. So it's 6.28 radians divided by a revolution. Revolutions cancel out. 1 times 6.28 gives you 6.28, and the radian remains. Now, just a reminder from before, remember a circle. A circle is equal to 2 pi. And what is pi? Pi is 3.14. So when you multiply it together, 2 times 3.14, you get 6.28. So just a reminder of where that number is coming from. And in case you forget, that's one way to remember it. Okay, so if we want to find angular speed now, we need to take our angular displacement. That's going to be what you have in radians. So put that 6.28 radians there. And we're talking about every minute, which we know is 60 seconds. Okay. and we're going to divide 6.28 divided by 60. That's going to give us 0.11, and then we just carry our units right over radians per second. And that's how you find angular speed. Alright, the key thing is to remember angular displacement needs to be in radians. Now what about angular acceleration? Alright, angular acceleration is equal to angular final speed minus angular initial speed divided by time. And again, you're using some interesting, actually Greek letters. This is alpha in the Greek alphabet. Alright, and we're going to use that instead of using A that we use in the linear problems. We're going to use alpha. And we know automatically when we see that that is, you're looking at something that's angular or rotational. In other words, it's going around. It's not going in a straight line, it's curving. Okay, so that's what A stands for. Alpha stands for angular acceleration. Now you have your omega here, that's final minus initial. Remember, these two have to be in the same units to be able to subtract them. Alright, and then you divide that by time. So the final is going to be the last angular speed in the problem, and the initial is going to be the first one. And when I mean the first one, I mean what you start with. Alright, the final is what you end with. Okay, we've already talked about the variables, alright, that we have here. Now what about units? Okay. Well, just like our acceleration before, alright, in linear we would have like meters per second squared. But remember, we're talking about angular distance, so it's going to be radians instead of meters. And look at the time is still squared. And then here we have our angular speed here, the final and the initial, they should be in the same thing. They should be radians per second. Now, if you're going to have radians per second, then you're going to want to have your time in seconds. If you, let's say you had radians per second and then you didn't make sure that this was in seconds, you come out with some strange equation. It could be like radians per second per minute or radians per second per hour, something like that. So you want them to match so that you can end up with seconds squared. Alright. For a problem, we have a wheel. Alright, it's turning at 340 radians per second. That's the first one, so that's going to be initial. And it accelerates to 400 radians per second in 30 seconds. 400 radians per second would be your final, alright, average speed there. And 30 seconds, that would be your time. Alright, now one nice thing here that you'll see makes it nice and easy. Look at, this is in seconds and this is in seconds, alright? And so your time is in seconds. Your initial and your final, they have the same units, so you can subtract them. Alright, you may not have thought about that before, but when you had algebra, you had to make sure that if you had variables, like let's say you had 10a and you wanted to add that to 5a, alright, they had to be the same, because if you had 10a plus 5b, you couldn't add them together. Right? They have to be the same. Alright, that's how the units work. So you have radians per second and radians per second, so you can subtract that, and then you divide it by 30 seconds. When you subtract it, you get 60 radians per second. Divide that by 30 seconds, and 60 divided by 30 is going to give you 2. Radians gets carried over here. Alright, doesn't have anything to cancel out with, and you have seconds here, but this is in the denominator, so it's actually like 60 radians per second times seconds. Alright, so what ends up happening, if you have seconds times seconds, you get seconds squared. So your answer here is 2 radians per second squared. The key thing is watch your units. And that's true in any problems that you have. That's what makes the difference between people who have less difficulty in some of the sciences, especially the mathematical sciences. The units are everything. You've got to follow them. They indicate what you need to do and how to get there, and you can check to see if you're correct. So they do make, a lot of sense to do that. Okay? Well, you have a worksheet to work on for this, so you have a good week.